Okay, so should I start?
No, let me, maybe Daniel, would you like to do the intro just to begin?
Yes, I thought that today was your turn, but I'm happy.
Oh, sorry. In that case, I will. I wasn't sure. Okay. So it's a pleasure to welcome everyone here in this next installation of our DD series, which is on frontiers in monitoring supported decision-making for structures and infrastructures. We have been running the series for a while now, and so this is actually our fifth talk, or fifth tandem talk, if I'm not mistaken. And today the focus is on machine learning driven SHM towards system level assessment. And we're very pleased to have as guests today Chuck Farrar from Los Alamos National Laboratories in the US, and Keith Worden from the University of Sheffield, who actually wrote the book on machine learning for SHM. I would like to start by, maybe I explained that this is a tandem setting. And so we start with one of our speakers for about a half an hour presentation. And then we go to the second presentation, and then there is a roundtable discussion where also the audience participates. For this reason, we ask you to also write your questions in the Q&A form, where we can pick them up also during the last session and bring them to the speakers. And without further delays, let me begin with the introduction of our first speaker for today, which is Charles Farrar. As I already mentioned, in the Los Alamos National Laboratory, leading the Engineering Institute within this division. The first 10 years of his career, he has been focusing on performing experimental and analytical structural dynamics studies, covering a wide variety of systems, including nuclear power plant structures under earthquake loading, as well as weapons components that are subjected to various operating environments. Since 1992, his research has focused on integrating hardware and software for structural solutions for structural health monitoring problems. And this is well documented in the variety of papers and diverse research output that has come out of his group. He has been recognized for his work with different types of awards, including the Los Alamos Fellows Prize for Technical Leadership, the inaugural Lifetime Achievement Award in Structural Health Monitoring, his election as a fellow in the American Society of Mechanical Engineers, and the list is endless, so I'm going to stop here.
Skip all that.
I will give him the floor to discuss structural health monitoring needs.
Okay, thanks, Eleni. So I'm going to start the talk, and then, as Eleni said, about hopefully a little less than a half hour in, we'll switch over to Keith. And so to get it started, when I was trying to put the talk together, I thought, what's the best way to convey this information to a highly educated international technical audience? And what I came up with, I think everybody would agree, it's a Trump rally is what we should be modeling here. And so my role in the Trump rally is to kind of be the preliminary speaker, maybe like somebody like Rudy Giuliani, and who will work the crowd up into an angry frenzy by showing them how the liberal academic community is to blame for all our structural health monitoring concerns. And by the time I'm done, I'm expecting people to be in the chat room chanting, "Lock them up," with regard to these people who we're going to blame for something. And then Keith's role will be to make structural health monitoring great again. And I think this is going to be a really effective way. You just see in the United States how effective these things are. But if I'm give full disclosure, Keith has too much integrity and self-respect to really buy into this approach. So we're probably going to do it a little bit more conventionally than that. So first of all, a lot of times when I'm with a group of people working in the structural health monitoring field, and if I actually ask them to define what structural health monitoring is, I don't get a consistent definition. So I'm just going to give you the definition that I use. And I would say it's a process of developing an automated online damage assessment capability for all types of engineered systems. Okay, and so you can think again about the analogy of a human information processing and sensing system that we try and replicate in all types of engineered systems with the goal of preventing this type of damage. This is the I-35 bridge in Minneapolis that fell down about 15 years ago or so. But I really emphasize that automated and online aspect, because that, in my opinion, is what separates structural health monitoring from traditional non-destructive evaluation. And you could probably even add further to that, trying to minimize the human in the loop part of the damage assessment process. And that's going to get into, that's where a lot of the machine learning aspects come in. Okay, so here's a structural health monitoring system. Here's a stonecutter bridge in Hong Kong. A lot of, look at 1,500 sensors of a variety of different types. I wanted to point out one thing with this though. These sensors that I've highlighted in red are not for the most part, are not monitoring structural response. They're monitoring the environmental and operational loading conditions that the bridge is seeing. And that's going to come in and be an important topic further down the line. The other point I would like to make here, when you look at a structure of that size, 1,500 sensors, which is a lot of sensors in an expensive system, really is still a pretty sparsely instrumented structure. Okay, so when did this whole idea of structural health monitoring begin? So I would speculate that that qualitative, acoustic or vibration-based damage or visual damage detection methods have been around as long as man has used tools. And over time, these methods have kind of matured, become a little bit more quantitative, and have evolved into what we currently know as non-destructive evaluation or non-destructive inspection methods. Okay, and really the forerunners for a lot of what our current NDE methods actually date back to the 1800s, but the real advances in traditional non-destructive evaluation have occurred in the 1940s through the 1960s. But some things that to keep in mind is these methods tend to be very local. They require access to the components. The system is usually taken out of service, and they are still somewhat qualitative. And in fact, some of them can just be thought of as enhanced visual inspection. Okay, so with that foundation, when you start to see the term structural health monitoring coming into the literature, it's usually coming in around the 1980s, I would say. And it certainly is built on the non-destructive evaluation technology. And it's really driven, I would say, you have a pull for this technology from various application areas. And I think the four big drivers have been the offshore oil industry, aerospace, civil infrastructure with particular emphasis on bridge structures, and rotating machinery. You also have some new technology emerging, which is really inexpensive sensing, processing, memory, and telemetry, and advances in machine learning. So you have this pull, you have kind of a push with this new technology. And about this time in the 1980s, the structural dynamics community gets involved with this. And what emerges in the first incarnation of structural health monitoring is really deterministic inverse modeling approaches to the problem. If you went to the first structural health monitoring, conferences that actually had the term structural health monitoring in their name, which really start about the mid to late 1990s. I would claim that about half the papers at those really early conferences were for some form of deterministic inverse modeling. Okay, so, how does this inverse modeling? So it works, and it works by comparing two models, one that's been correlated to undamaged data with one that's been correlated to damaged data. So this is how we got involved in structural health monitoring in the early 90s. We had this bridge in Albuquerque, New Mexico that was going to be torn down, and we were given the chance to damage it, as you can see here, and look at various vibration-based damage detection methods on this full-scale structure. We had about a 2-week window before they were going to tear the bridge down to do this. So so we did experimental modal analyses on the undamaged structure, and then after various levels, and then built finite element models and correlated them with the undamaged data. Then we introduced damage, and again repeated the measurements, and then updated our finite element models based on the undamaged data. And then we compared the stiffness indices of those two models to give us an indication that damage was present, where the damage was, and an estimation of the extent of damage. So that looks like a really good approach, but there's some real big problems with this approach. So first of all, you're using linear models to model the structure before and after damage. In this case, that's appropriate. That cut that you can see there just changes the geometry of the structure. Under the loading that we had available, which, as you might imagine, there's no traffic loading when we're making that cut. We just have a shaker mounted on the structure. The shaker didn't have enough power to make that gap open and close and produce nonlinear response in the system. So that part's not too bad. But the other part is, look at the number of degrees of freedom in that experimental modal analysis. There's only 26 degrees of freedom, and there's a couple of 10,000 degrees of freedom in that finite element model. That degree of freedom mismatch is a really big issue. And also, there isn't just one resonant frequency and mode shape. Those change with environmental and operational conditions. So which one do you use to compare? That's a real question. Okay, so things start to change around 2000, and I would say the group at Los Alamos as well as Sheffield start to pose this problem as a problem in statistical pattern recognition. And it really emphasizes the issue that this damage detection problem is not a deterministic problem. Okay, and once you accept that structural health monitoring is not a deterministic inverse modeling problem, I guess it would still be an inverse modeling problem potentially, but not a deterministic one, you can bring a lot of tools from other technologies to bear on the structural health monitoring one. So certainly things developed for radar and sonar detection, speech pattern recognition, machine learning, which is the big focus of this series of talks. Some of the things that have worked best for us are things that have come out of econometrics, okay? And none of these methods preclude the use of physical models. And in fact, you're always going to be better off if you have a physical understanding of how the damage is going to alter the dynamic response of your system. Okay. And I would say as you start getting to this time frame a little later, what you see at the structural health monitoring conferences is a real back off in the papers on inverse numerical modeling approaches to damage detection, and they're getting replaced by what I would call ultrasonic guided wave approaches. There's an awful lot of those. By that definition I listed on the first side, in most cases, I would not consider ultrasonic guided wave approaches structural health monitoring, because I don't think they really meet that online automated criteria. I would think of them as still a form of non-destructive evaluation, albeit that that's kind of a gray area. Okay, and some fundamental axioms were proposed as a result of this. Okay, so how do you actually implement that paradigm in a structural health monitoring setting? So I think there's 4 steps that you have to include, and whether people explicitly call them by these names, that's another issue, but I think that you really have to have all of them. So the first one I just refer to as operational evaluation. You have to define the damage you're trying to detect. If you can't do that and you put sensors out there and identify damage, you're going to be somewhat lucky in doing it if you haven't defined the damage up front that you're trying to detect. You're going to have to do some data acquisition. You're going to have to put sensors out there. And then you're going to have to translate that raw data into information about the damaged condition of the system. And we usually do that by extracting some features from the data that are correlated with damage and usually of a lot lower dimension than the raw data that we've acquired. And then subsequently, we're going to do some kind of statistical decision making to classify those features as damaged or undamaged. Inherent in both the hardware and data analysis portions of the process are the ideas of data cleansing, data normalization, data fusion, and data compression. As I've listed here, you can do those in hardware or software. In the reality, you probably do those in a combination of the two. Okay, so where are we at right now? And so I would say in certain areas, structural health monitoring, although it doesn't go by that name in some of these areas, has made the transition from research to practice. And the big one is condition monitoring of rotating machinery and the health and usage monitoring systems that are used on rotorcraft. Okay, which are closely related to rotating machinery monitoring. There's a lot of new applications for structural health monitoring that are continually being reported. And I've just given a laundry list here of different ones. Mike Todd, who's talked earlier, is doing a large project on inland waterways right now. We've looked at some of the telescopes that we actually build at Los Alamos. Mike and I have actually gone down to that mine in Chile that you see over on the right. So a lot of different application areas and more conferences, dedicated journals. So slowly the technology is really starting to mature, and there's a lot of research going on around the world. But the reality is, in most cases, the state of the art for doing real world damage inspection detection is visual inspection, and then sometimes supplemented by local non-destructive evaluation. So again, let's look at this issue with the rotating machinery, where the structural health monitoring has made the transition from research to practice. So, and what are some of the reasons for that? In my opinion, first of all, in most cases, there's not a first order life safety issue that you have to worry about. Whereas if you're trying to implement this in aircraft and rely on it in an aircraft setting, certainly there would be a first order life safety issue. The damage often occurs on relatively short time scales. And coupled with that, then it's somewhat straightforward to show an economic advantage provided by the structural health monitoring. you can make a business case, if you will. And the current inspection methods prior to these are not adequate. You don't need to locate the damage. I think for the most part, damage types are known. And in some cases, damage data may be available. And as the picture shows, you can get away with a really limited number of sensors. And oftentimes this is a rotating machine in a semiconductor fabrication facility. Oftentimes they're in places with pretty well-controlled environments. Okay, and so then other successes, again, which would be related to the rotating machinery one, are the rotorcraft health and usage monitoring systems. Okay, so what are some challenges? Why hasn't the structural health monitoring in general been widely adopted? So, and I think there's a lot of reasons for this, and these reasons then also point to a lot of research challenges for the structural health monitoring community. So, first of all, I would say there's no widely accepted procedure to demonstrate the rate of return on investment in a structural health monitoring system. Okay, and this is a really big hurdle. If you want owners of infrastructure to buy into it, you have to demonstrate that rate of return on investment. Okay, and that really falls under that first operational evaluation step that I talked about in the 4-step paradigm. I think there's what I list here is St. Venant's principle, which states that discontinuities in a structure that only are going to influence the local strain field around that discontinuity. And that poses some issues for data acquisition and the number of sensors we need to employ. I don't believe that there is any accepted sensor design methodology. If you say, I have this structure and I want to detect a crack of a certain size, there's no design methodology that says, here's how the sensors I choose, here's how I establish their signal to noise ratio, here's how I place them, that type of thing. All the sensor design, to my knowledge, is done in a one-off manner. And I put the next two in red because I think they're some of the biggest challenges. So understanding how the damage sensitive features change with changing environmental and operational conditions. Okay, if you can't understand this, you'll really run the risk of getting false positive indications of damage just simply because you're measuring the structure in a different environmental and operational condition, not because damage is present. Also, it's very rare that we actually have data from the damaged condition to use in our decision-making process. Almost all structural health monitoring has to be done in an unsupervised learning mode. All right, so then there's some other ones. How do we set classification boundaries when we're trying to do our decision making? That's always going to involve trade-offs between acceptable levels of false positive or false negative indications of damage. And if we're going to really do this autonomous online monitoring, we're going to get large volumes of data. And we have to think about how are we going to manage all that data. And I think one thing that we can do is look at how others manage large volumes of data. You could think of credit card fraud detection as kind of an anomaly detection where you have lots and lots of data and you're looking for the needle in the haystack, if you will, where there's some indication of fraudulent behavior in this huge volume of data that's coming in each day. And if the credit card companies were willing to share how they do that, that might be something that the structural health monitoring community could really learn from. Okay, So, and let me just give an example of this issue about the operational and environmental variability. So here's a bridge in southern New Mexico that we had the opportunity to test a number of times. So we did a test every 2 hours for a 24-hour period. And you see in blue there that the frequencies that we identified for the first mode change about 5%, depending on whether you're doing the measurement at day or night. And it turns out that if you went back to that I-40 bridge where I showed making the cut in the girder, and that when we made the cut all the way down and across the bottom flange, that made a 7% change in the resonant frequency. So the changes that you're seeing due to environmental variability, and this bridge is particularly susceptible to environmental variability. It's located in a north-south orientation, and the sun comes up and hits it on one side in the day and starts heating it up, and then that changes in the afternoon, and then in the evening when the sun is down, it kind of becomes more uniform. What you see in red is the temperature differential across the bridge, and you can see that those changes in resonant frequency are really well correlated with the temperature differential. If I had plotted the absolute temperature, there is no correlation that is evident. It's the temperature differential. And if you can see this effect in the mode shapes, the bridge is symmetric about the center line. We should see a nice symmetric first bending mode, but you see it skewed to one side in the morning and the other side in the afternoon. If you can't account for this variability, again, you'll run the risk of getting false positive indications of damage. All right, some other challenges. I think there's a big discrepancy on how researchers develop solutions to structural health monitoring problems and how industry develops solutions to structural health monitoring problems. So researchers tend to define a methodology and then shows that it works on some generic problem. And often they match that generic problem to the methodology. So an example of this that I've seen umpteen times in technical papers is they develop a method, and this would be particularly true of the inverse modeling approaches. And then what their damage is going to be to reduce the modulus in one of the elements of a numerical simulation. Now, I know of no damage that reduces the modulus in material. And the only thing that I know that reduces or changes modulus is thermal effects and maybe irradiation in some cases. Okay. So that's an example of where they match the damage to the methodology that they've developed. Industry would tend to define the specific problem that they're trying to address, and then develop a solution to that specific problem. Okay, it's almost 180 degrees out of phase of how the research community addresses problems. And I would say few, if any, journal articles that I've ever read start by defining the damage they're trying to identify. They always start by defining the methodology. Okay, and again, I think that's 180 degrees out of phase if you're trying to implement this in real world systems, how you would go about the problem. There's also this issue that I call the structural health monitoring catch-22 that I have to worry about because that dates how old I am, and some young people might not know that term from a book and then a movie that I think came out like in the 1960s or early 70s. So owners won't invest in this technology until it can be demonstrated on real world systems. But nobody's going to give you a real world system of any economic significance and let you damage it just so you can demonstrate your structural health monitoring technology. This relates back also to the issue about that we have to do structural health monitoring in general, in most cases, in an unsupervised learning mode. So a few others, I think challenges for university researchers, they typically don't own the systems that they might be trying to develop a solution for. that can limit things like access to the data, publishing the results, things like that. I think you also need to have people who can vision an entire system life cycle and who can integrate diverse technologies. I think also we have to look at university education, and is it evolving to address the needs for these really what you need in structural health monitoring is multidisciplinary technology developers and integrators. And most advanced degrees are awarded for doing a deep dive in a narrow area of technology. So this is, again, kind of and they're certainly usually not awarded for doing technology integration. So, so what I think is needed is simple, reliable, adaptable, low maintenance structural health monitoring systems. I don't believe a system will ever get out there if it requires somebody with a PhD to run it. Okay. We need to be able to qualify the probability of detection and the probability of false alarm rates under all the anticipated sources of operational and environmental variability. But to do that, you can't come up with a false alarm rate if you can't define the damage that you're trying to detect. Okay, and we need a lot of credible verification and validation studies. And we have to be able to perform robustness assessments related to uncertain portions of the structural health monitoring process. Something that I don't think the community looks at and maybe assumes maybe that the computer science community is going to look at is you have to have information security. And I think what is a real need is codes and standards, and that's starting to happen, and that's really a sign of technical maturity. Okay, so there's some in the aerospace community. I know at least in China, they have developed ones for civil engineering applications, but those need to evolve, and they help with litigation issues. All right, so at the end of the day, I don't believe structural health monitoring will become mainstream unless it can become an integral part of the lifecycle engineering paradigm. And so this system design V, I actually got from a presentation I saw Boeing engineers make a long time ago of how that you start with the concept of operation, translate that into design requirements, then start testing, assembling the systems, building them back up, and so forth. And I just put in red where if structural health monitoring were to become part of this process, it has to come into almost every step of this process in one way or another. And so I'll just conclude my portion of the talk by saying although I've highlighted all these challenges, I'm still, really excited about the structural health monitoring because I think it's really part of what I would consider an engineering grand challenge problem. And I would state that grand challenge is the ability to provide cradle to grave system state awareness for all types of engineered systems. And that really means having complete knowledge of a system throughout its life cycle. And to do that, you're really going to have to design system functionality in at the material and manufacturing level. You're going to have to monitor, control, and assess in-service system condition, and that's where the structural health monitoring comes in. And then you're going to have to do intelligent life extension and system retirement. And again, that's where the structural health monitoring and ideas of damage prognosis comes in. So that's the end of my portion of the talk. You should be really mad. I haven't seen in the chat anybody saying lock them up yet, but hopefully somebody will break the ice and do that. But at this point, I'm going to, unless, I don't know if what the standard is here, if you stop with some questions, or do I just hand it off to Keith?
We hand it over, but maybe first Daniel does an intro of Keith. or as you prefer,
Yeah.
actually.
Yes.
Okay, so I'm going to stop sharing my screen.
Yes. Thanks a lot, and I hope, and I'm sure nobody will shout, lock him up, but maybe. And I think people did get excited, and I remind everyone that there's this Q&A button at the bottom of your screen. Use that to pose your questions, and we will pick them up after Keith's presentation and have a joint discussion. So with this, I like to introduce, and it's my great pleasure and honor to introduce Keith Worden as the second speaker. He actually hardly requires any introduction, I believe, but the protocol dictates that I do that. So Keith is with the University of Sheffield, where he heads the dynamic research group. Which is interesting, he has a background as a theoretical physicist, moved into mechanical engineering. And what I learned is that later in his life, he did a PhD in mathematics. So a well-rounded scientist. His research is concerned with applications of advanced signal processing and machine learning methods to structural dynamics. I think mostly working in aerospace industry, but working with other industries as well. He has a long list of honors, including lifetime achievement awards that I will not I will not go through now, because as I said, his research and the literature have been inspiring and I think shaping this community for a long time, including the mentioned book that he was co-authored by Chuck and Keith together on structural health monitoring and machine learning perspective. And I really look forward to your talk as well and to the discussion we'll have jointly afterwards.
Okay, thank you, Daniel. That was probably kinder than I deserved. I'm going to try and share my screen now. Can people see my slides?
Yes, now?
And if I go to full screen, is that okay?
Looks
Perfect.
good, yeah.
Oh, okay. So I think first of all, I'd like to thank Chuck for casting me in the role of Trump there. That wasn't something I was expecting. And yeah, cheers, mate. I want to talk about some aspects of SHM that make contact with some of the other talks that have been in this series, and also trying to keep contact with what Chuck said about the challenges to SHM. And so I want to talk about a way that we've been looking at SHM, and also we're trying to look at population-based SHM now. So that the decision aspects of the framework are at the forefront. And in order to do that, we're going to look at a probabilistic risk analysis viewpoint. So I've got to acknowledge Aidan Hughes here, who's my colleague in Sheffield, who did all of the heavy lifting on this work. I have got way too many slides as usual, so I'm gonna alternate going so fast that things are incomprehensible with just skipping things altogether, and we'll see where we get with that. You will probably want to lock me up anyway. The motivation for this probabilistic risk assessment viewpoint, the probabilistic, I think, goes without saying. We've already said that we want a statistical pattern recognition approach to SHM, ideally, because it deals with uncertain quantities. But the risk was a new thing for me, despite the fact that Chuck told me I should look at probabilistic risk assessment 15 years ago. Right? It took a while to filter through the fog. if SHM is going to be useful, okay, in the management of our structural assets, it's got to guide or support decisions. And if we're going to be principled about that, we've got to base those decisions on risk or utility, not just probability. Because risk encodes both the idea of probability of something happening and its possible consequences, its possible costs. And risk is nicely represented by this quantity expected utility, where expected utility is, well, it's the expected value of the cost of an action. So the probabilistic side comes in through the expected part of that, and then the cost comes in through the consequences comes in through the cost. And up to now, SHM has mainly been focused on the probability aspect of it, which was hard enough actually, and less on the consequence. But this isn't a general situation. A lot of industries have approached asset management from a risk perspective for a long time. And particularly the aerospace and nuclear industries have adopted this probabilistic risk assessment strategy. And the US Nuclear Regulatory Commission and the International Atomic Energy Agency laid down the groundwork for this decades ago. I mean, the first report I've got for this was in 1975, and it's by no means the first one. So I want to present here some of the ideas about mapping probabilistic risk assessment into an SHM decision framework. And we're not claiming that all of this is novel. There are precursors to all of this stuff all over the place, but we're trying to build a consistent framework here that will also address some of the SHM challenges that Chuck was talking about. So we don't want to throw anything away that has been useful. And so I want to keep, obviously we all want to keep all the bits of SHM that work, particularly the bits of data-based SHM, you know, these technologies that we've adopted from machine learning and from these other different areas of science as well. Like Chuck said, econometrics has turned out to be really useful sometimes. And this four-stage approach to SHM as a pattern recognition problem, it's Chuck's formalization into a four-stage problem. We have the operational evaluation stage, data acquisition, feature selection, and then statistical modeling. Now, I was going to elaborate about operational evaluation because I think this is one of the important things we have to deal with. The rest of the stuff sort of goes without saying. It's the normal usage of the terms in pattern recognition. But in operational evaluation, you have to answer some questions about the implementation of the SHM system, the design of the SHM system, ideally with the design of the structure, although sometimes we're stuck with retrofitting. And there's this big question about what is the economic safety justification for implementing a system relating to this cost benefit analysis that people very rarely do. And we've got to answer some serious questions about what type of damage we're looking for. Some approaches will find some sorts of damage, but not others, and so on. What are the environmental and the operational conditions that we're going to work under? Because this is going to create non-stationarity, and non-stationarity is bad news. And how is the environment going to limit the data acquisition? It breaks down into a lot more detailed questions than this, but it's all about understanding what your problem is. Once we've decided what the problem is, we've got to build the technology to solve that problem. And it's useful to actually organize the types of SHM problems that we might get in order of severity. So Ritter's hierarchy is an old way of looking at this now, but it's still a useful one. And it ranges from questions about simply having damage in the system or not, through where is the damage, what type of damage have we got, through to prognosis. How much useful life have we got? Actually, prognosis is a much more general question than that. And roughly speaking, this is in order of difficulty. Now, probabilistic risk assessment, as formulated within the nuclear industry, is also a multi-stage process. And we've taken these stages here from some of the main guidance documents in that field. And they also start off with operational evaluation, really, because this is just a synonym for the initial information collection. And then there's a process of modeling, a process of acquiring data and interpreting it. And then at the end, there's this stage of consequence analysis. And consequence analysis is the thing that doesn't map into the SHM problem quite so well at the moment. The levels 2 to 5 here loosely work their way into the SHM framework through feature selection, data acquisition, statistical modeling. So taking all the things so far into account, we're going to propose a general scheme or process for risk-based SHM. And we're going to keep operational evaluation, and we're going to keep this process of data acquisition, feature selection. And the changes that we're going to make is that we're going to pull out of operational evaluation and formalize the failure mode modeling. And we're going to formalize the decision modeling, because that's going to fit into the process as an integral part of it. And then we're finally going to need consequence and decision in there. And these decisions are going to be based on risk. Now, in order to embed all of this stuff into a nice general mathematical framework, we're picking probabilistic graphical models here, which other people will call Bayesian networks. It's okay, the same thing. And these are really good from the point of view of probabilistic analysis, machine learning, because they're a very versatile framework for learning and inference. So, and people have been using the machine learning stuff in SHM for 20, 25 years, and probabilistic graphical models are all over the literature. They're not quite the same things that we deal with in probabilistic risk assessment, though. These have traditionally been based on logical structures, event trees and fault trees. If-then rules, if you like. And they're made into probabilistic objects in risk and reliability theory by introducing the concepts of reliability. So the first thing we want to do, if we want to map PRA into SHM, is turn objects like event trees and fault trees, which are stories of consequences, if you like, into probabilistic graphical models. And fortunately for us, there were already some really good ways of doing this. I think the two main references that I'm aware of, we're aware of, are those by Bobby O and his co-authors in 2001, and Shankar Mahadevan, who spoke earlier in this sequence as well. And these are all about Bayesian networks in a system reliability context. So I'm going to give a simple motivating example. And this, like nearly everything in this presentation, it's really Aidan's ideas. So let's look at an event tree, okay, a sequence of events with outcomes. We start off with an initiating event, and in this case, we're going to look at what happens if you jump from an aeroplane. and you intend to save yourself with a parachute. So the initiating event is that you jump out of the aeroplane. And then the important event for you next, the top event at this level, is to activate your parachute. Now, this may be automatic or you may have to do it manually, but you will want to activate your parachute. If your parachute works, these are where the if-then rules comes in. If your parachute works, the whole thing's successful, you float to the ground, no problems. If your parachute fails, you then have a reserve chute, which you can attempt to activate. And I like the way that Aidan's put the adverse event here is injury. The adverse event is probably a lot more dramatic and messy than that. But if the reserve chute works, then the system's successful. So you've got a series of if-then rules. From the point of view of a logical structure, we can code this in terms of AND gates and OR gates, and they can be incorporated in a fault tree. Subsequences can go into subtrees. So, for example, we might have a whole series of events that lead to the reserve parachute failing. Okay, so basic events here are that the altimeter malfunctions. Okay, so it doesn't open until you hit the ground, or you've got a dead battery, so it doesn't automatically open. These feed into whether or not the parachute actually gets deployed or not. Whether it gets deployed or not will depend on whether it gets activated either automatically or by you using the ripcord, which you could, that might not work either, in which case the parachute's not deployed. The other thing that can go wrong is it gets deployed and then something else happens, like it gets tangled. The ultimate result is that your reserve parachute fails and splat. Now, these Boolean structures, these logical structures, we want to get them into the form of a probabilistic structure in order to map it into the sort of algorithmic frameworks that we're familiar with SHM. And so, and the rules for this are reasonably straightforward. You take locally some, or this is an OR gate, for example. So C is going to happen if A or B happens. This is really straightforward to map into a Bayesian network. And a Bayesian network is really about how probabilistic variables influence each other. And arrows essentially say that a variable C is conditional on a variable A. Now, clearly, C depends on A or B happening, so it's conditional on them. So that's the way the arrows point. But in this particular case, we can calculate conditional probabilities just by initializing them with the truth table for an OR gate. Okay. If A happens, we get C. If B happens, we get C. We can translate these into probabilities. So in an SHM context, we're gonna see these conditional dependencies come through lots and lots of different pathways. But one pathway that's important here is going to be the idea of a failure chain when we're trying to build a fault tree in SHM. We're going to give structures a hierarchical organization in terms of components, joints, and substructures, etc. And so when we get a failure at a component level, that might or might not lead into a failure at a substructure level, and that might or might not lead into a failure at a structural level. And so here's a sort of hierarchical representation where we've got two components at this level L, joined together through some joint, and that forms a substructure, S13. That might be joined with other substructures or even more components to generate another level of substructure in, and then eventually we get to a structure. Now this looks a bit of a mess really, but all we're saying is we're trying to back out how structures can fail because parts of them fail, because things go wrong in joints or components, yeah? And then this gets mapped into a fault tree, yeah? Substructure S13 will fail if component 1 fails, component 2 fails, or the joint between them fails, yeah? And then ultimately the structure fails. This is what this top event is. Now, following the rules that we just talked about in terms of embedding these rules into probabilistic graphical models, here is the corresponding graphical model for that particular structure. And we're going to give state variables to the conditions of all of the components and the joints. And you can see the conditional dependencies here. The health state of this substructure here depends on the health states of the two components it's made from and the joint that puts them together. And everything depends on some overall health state variable that we're going to try and get from data, okay? We're going to try and infer H from some machine learning algorithm based on data. That will tell us all about these health states, and ultimately that will tell us what the probability of failure is. Huh? And we're not quite there yet, because we want to include decisions in this framework. Now, normal probabilistic graphical models are just built of probabilistic variables with their conditional dependencies, and this thing expresses some massive joint distribution of all of these variables. And based on whether or not we can see some of these variables, we might or not be able to infer the states of some of the others. That is the basic problem in a graphical model. It's not quite what we need here, though, because we want to make decisions. So we've got to include that into the framework. And the way that we do that is with two different types of nodes into the probabilistic graphical model. There are utility nodes that tell us what the cost of certain actions are, the cost of certain variable states, and decision nodes that are going to choose an action based on the probabilities of things happening and the cost of these things happening. And a policy will be a way of processing all of this data from all of these things to yield a decision, an optimal decision. Okay, and that decision will be chosen to minimize risk, yeah, or to maximize utility. These are the same things. So a nice simple example of an influence diagram is this. So this is a graphical model again, but it's got two random variable nodes. It's got a decision node and it's got a utility node. And so the question that we're asking here is, given the uncertainty in the weather and the fact that I've got a weather forecast, should I go for a walk or should I stay in and watch the television? Now, the weather condition has two states, bad and good. And the weather forecast has two states, bad and good. And the possible actions are watch the telly, go for a walk. Now, we want to choose this decision based on utility, the cost of the decision. And the way that this works here is fairly simple. If the weather is bad, I really should be choosing to watch the television. If the weather is good, I want to be choosing to go for a walk. But I don't know what the weather is going to be. I only know what the forecast says it's going to be. That's like an observable. So I'll make my decision based on the forecast. And then there'll be some sort of cost associated with what happens, right? So if the forecast is good, my decision will be go for a walk. Now, if I go for a walk and the weather is actually bad, I'll get negative utility. I'll get wet. I'll be miserable. If the weather is good and I go for a walk, I'll be really happy. Positive utility. If the weather's bad and I decide to watch the television, positive utility, and so on. Okay? Now, there's nothing massively interesting about this particular example yet, because if the forecast is good, my decision is to go for a walk. Okay? And this relates to, there's no learning problem here. The weather forecast is just binary. But suppose the weather forecast gave you a probability between 0 and 1 that the weather was going to be bad. In that case, you'd need to choose some threshold on the probability of bad weather before you would make a decision to stay in and watch the television. And that threshold is a learnable parameter in this context. And that's what we've got to get from the data. Now, this is the analogous type of process for that SHM problem that we've got. We're going to measure some feature data. We're going to infer some health state from that data. This is the standard SHM problem. We're going to classify the thing. And then on the basis of that, we're going to work out whether or not the structure fails or not. And so while this looks like a mess, this whole bit here from nu of t up to u of ft is really just the weather forecast. Yeah? That's the thing that's telling me whether the weather is going to be good or bad or not. What the system actually does is what the weather does. And so my decision here will be, keeping it simple, do nothing, perform maintenance. Now, doing nothing doesn't cost anything. Doing maintenance costs something. It's got negative utility. But if I do nothing and the system fails, that has a lot of negative utility. Okay, so this is very much actually like the go for a walk, watch the television problem. It just looks a lot more horrible. So we need a number of ingredients to do this. You know, when we're thinking about SHM as a temporal problem, we don't only want to decide today whether we should do something or do nothing. We're going to need to make that decision every day. And in the meantime, the structure might be degrading. We might be going from some health state T to a health state HT plus 1 the next day. So we need a transition model, and we need all of these other ingredients. And the basic principle is that we can do these things, okay, with a risk-based formulation. I'm going to jump straight to an example here, right? So this is a nice static example in some ways. Let's imagine we've got a two-dimensional 4-bay truss made out of 20 members. And we consider 8 of them to be critical. We can measure strains in this structure by putting some known loads on the structure and measuring the strains, and then there'll be an indicator of the health. And the idea is going to be that we want to diagnose from strain gauges on all of the horizontal and vertical members what the condition of the diagonal members are. And if a diagonal member fails, we've got redundancy, we're going to be okay. But if both diagonal members in a bay fail, the bay fails and the structure fails. Yeah. So we've got some important conditionals here. The health state structure is the integrity of the diagonal members. Okay? These are health states. And the important conditionals are going to be how the failure state of the whole structure depends on what is happening in the bays, the health states in the bays. And the health states in the bays depend on the diagonal members in the bays. Okay? So these are all built into a fault tree that looks like this. If a bay fails, the structure fails. In order for a bay to fail, both diagonal members have got to fail. That's an OR gate. We get failure if any of the bays fail. This is an AND gate. We get failure of a bay if both diagonal members fail. That maps into a Bayesian network quite nicely. We need utilities now because we're going to build these influence diagrams. And we're going to say that the cost of no failure is a positive utility. It's not a cost, it's a benefit. But if we get failure, we've got a very large negative utility. We've also got a cost, a utility associated with the decision, and the decision is going to be do nothing, perform maintenance. Doing nothing doesn't cost us anything. Doing maintenance costs us quite a lot, but nowhere near as much as allowing the structure to fail. Okay? Now, I could put this all in a big Bayesian network and try and infer this all from data directly using algorithms for inference in influence diagrams. But we simplified this and we've built this whole subsystem here, this classifier offline using a neural network. So we've got a neural network that takes all of those horizontal member strain states and predicts the diagonal member strain states, which is the health state of the structure. And so this classifier is doing all of our health state information. It's our weather forecast. We've got a neural network weather forecast. And then the whole set of ingredients, which includes a failure model, a transition model, the classifier, the decisions and the utilities, get built into a big influence diagram, which in this case is a limited memory influence diagram. And you can train these things with the same sort of algorithms that you just train vanilla graphical models. So there's a variation on them, a junction tree algorithm, a message passing algorithm. Now, the static classifier, the neural network algorithm, is summed up in this confusion matrix here. And the diagonal elements are correct classifications. It's the usual sort of confusion matrix. It's doing fairly well, okay? Overall, it gets a 60% chance of classification correctly. We've deliberately not used a perfect classifier here because that wouldn't be interesting, okay? So we've got a 60% accurate classifier. There's 8 possible states here, so random guessing would give you 12.5% right answers, but we're getting 60. So it's a good algorithm. Now, what we want to do is take the classifier, the weather forecast, embed it in this big influence diagram that considers what happens over 3 days. Yeah? We have to make 2 decisions about whether to do nothing or to perform maintenance. And that's based on utilities. Okay? We want to assess this in terms of how well it's made decisions, not how well the probabilistics have gone. on their own. So what we do is we adapt the confusion matrix idea to decisions. And instead of saying, okay, we go into the diagonal if true class 1 gets predicted as class 1, yeah, we build this decision confusion matrix by saying we add 1 here if we made the decision do nothing when we should have made the decision do nothing, when the system was undamaged. And we make the decision perform maintenance when we should have performed maintenance, when the system was damaged. And so you can see that even though the classifier was only 60% accurate, we've actually arrived at a decision maker which is 93% accurate. It makes the right decisions 93% of the time. For this problem of over 3 days saying, do we do nothing? Do we perform maintenance? And that's for a specific cost of a failure. Okay. Now, I understand that that's been really, really technical, but I have wanted to get across the idea that although there is maths at all stages of this framework, it's maths that works, okay? Assuming that we can measure informative data, assuming that we can do the inference in reasonable time, which we can actually formulate SHM problems in terms of decision outcomes, in terms of risk, in terms of utility. And it works very well. So what we're doing at the moment, and I need to skip past this, I think, because I'm not leaving much time for questions. We can move this from, because this has been based on a level structure, components, substructures, structures, we don't really have any conceptual problems extending it to populations of structures. Yeah. Now this brings us to the general ideas of systems, but if we're talking about something like all of the wind farms that a company owns, and the smallest unit that can go wrong is a gearbox or a bearing, we actually need a system of systems of systems of systems of systems of systems, okay? But I will not dwell on this. So one of the interesting things that happens when we start to consider populations is that we can build into our utilities and our decision processes the idea that we might let a structure fail because we will get so much useful information from it that the classifiers and the decision makers will be refined and will save structures in the future. So we can formalize the idea of sacrificing structures in this formalism. So I've potentially pitched that quite badly in terms of the sheer amount of maths in it, but I hope I've got across the idea that we can build SHM from a decision theoretic viewpoint. We can deliver decisions rather than condition assessments fundamentally, just probabilities of certain structural states. And that's important. And also we can extend this idea to populations. And the reason why that's important is because of this idea that Chuck mentioned earlier, the challenge that we don't often get damage state data for structures. But if we have populations of structures, we have damage state data for some of them, and we can use that to leverage information from the others. And so all of this stuff gets all folded together, and hopefully at the end of the day, we solve some of these fundamental challenges. So I've got to finish up with some acknowledgements. Obviously, the foremost acknowledgement is to Aidan. We've got to thank the EPSRC, which is the UK funding body, for giving us various grants to do this. I have to thank Chuck because, well, basically all of the ideas that I ever try that work come from Chuck, to be honest. The ones that don't work, I can take credit for. Mark Bateman from EDF is a colleague who's given us a lot of insight into probabilistic risk assessment, and he works in the nuclear industry, so he has to worry about this sort of thing. And in the dynamics group, well, we've got to thank a number of our colleagues who've contributed to this work. So Rob Barthorpe, Paul Gardner, Nikos, and Lawrence Bull. And so I go to my question slide. This is Ash, my cat, pretending to be a toy, which is a trick that he picked up from watching ET, actually. He's only started doing that since we watched ET, but there you go. He's a bright cat. I'm going to shut up now. And I'm going to stop sharing my screen.
So thanks a lot to both speakers, and I think we got a lot of input for discussion that we'll still have. There have been already questions in the audience.
Yes, and I have to say Chuck was very active in replying, so many thanks for solving already some of these.
You might pick up one or two of those as well. Maybe my first question is, did Ash like E.T., the movie?
He did.
He did? Okay, good.
Yeah. He's not a big fan of science fiction as a rule, but he liked E.T. But E.T. crosses a lot of genres, doesn't it?
It does. So maybe I think it was very good because we had two kind of very different perspectives on the topic, and yeah, I see that there was multiple questions already answered, but maybe
they're not such different perspective. It's just that Chuck communicated is better.
I think you stayed true to what you mentioned. A lot of the problematics identified by Chuck in the beginning, and then some perspectives on how math can indeed solve problems in the end by Keith. So that's appreciated.
Yes, there is also the great idea, the kind of the great concept, the big picture, and then kind of also on the other hand the messy reality. And but maybe let me start with a question in the Q&A that has not yet been answered already, and that I think relates also to other questions and touches upon both presentations, which is this kind of need for being able to demonstrate the rate of return of on your investment, and what Pablo asks is basically the fundamental problem that before you put your SHM, it's hard to quantify your likelihood or basically how good it is, how good your system will be in picking up a potential damage that you might not even yet exactly know what it is, but without being able to specify that, you have a hard time to demonstrate your rate of return. So what is the solution?
So I can just given that the resources would be available, this is a role for where physical modeling can come into the process. Because if you don't have the actual measured data, the next best thing is to generate some simulated data that's as close to what you're anticipating as possible. Because I don't see how you're going to get that. And again, in one of the responses I had to one of the questions, which I should apologize, I didn't know the etiquette. I was assuming I was supposed to be responding to those while Keith was talking. I didn't realize.
No, you can do that good. Actually. That's a good.
Okay. I thought maybe we were supposed to wait till the end, and if that was the case, I wanted to apologize for not knowing the drill. if you will. But again, I think short of that, and I think where it also comes in, you're going to have to design the sensor system at some point. Okay, and more than likely, you're not going to have damaged data for the design of the sensor system either. And that, again, is a place where numerical modeling can come in and at least provide, some indication of, do you have the appropriate sensor layout? Do the sensors have the appropriate sensitivity? Are you monitoring the appropriate bandwidth? All those issues that you have to address when you're designing a sensor system. Really hard to address with limited data that doesn't include the damaged data.
So if I can just have a go, Chuck, this is another thing that you can potentially address through the population-based approach. Because ultimately, in the population-based approach, the idea is to transfer inferences from one structure to another. Yeah. So say, if this happened to this structure and this was the result, and this thing over here, the information, we do that with transfer learning. The neat thing about this, and I think one of the things that is a step forward potentially, is that your structures in the population don't have to be real structures. They can be models. And if you take a population-based approach, you don't have to have perfect correspondence between the models and the structures. You don't have to update the models and believe that something that happens to the model will happen to the structure. You only have to have transferability. You have to have them close enough to each other that something that happens to the model can happen to the structure. And I think this is one of the potential benefits of taking that approach. And I agree with Doug completely about the pointlessness of reducing the Young's modulus in a finite element model in some ways as trying to model real damage in a real structure. But if you're not looking for correspondence, if you're not looking for exact correspondence between the model and the structure, all you need is for some things to have similar consequences. And if damage in a real structure drops the natural frequencies, and reducing the Young's modulus in a model structure drops the natural frequencies, then the rough correspondence is something you might work with, but you mustn't believe that you're observing reality from the model. You're just seeing a different thing that can happen, and you might be able to make some deductions from it. Does that make sense?
It does, but maybe also we add that in some cases, this is not as unrealistic as it sounds, because if you think of cracking as an instance of damage, if we think of concrete structures, then reduction of the equivalent modulus is not far from what really happens in that case. So yeah, I agree that actually the correspondence is important, but it's also, maybe we don't, a simplification sometimes is allowed and could reflect the actual observed phenomenon.
Well, they both produce localized increases in flexibility, but if you look closely, they don't do the same things. You know, a real fatigue crack will open and close.
Correct. Yeah. This is,
and so it doesn't just depend on it doesn't depend on one thing looking like the other. It depends on what you are looking for. You know, so if you know from your real structure that a breathing crack will generate certain nonlinear artifacts, and you can spot those things, you'll never see that from the model where you just reduce the Young's modulus. It will be useless to you. So you have to have correspondence, but it doesn't have to be perfect.
Maybe we ask Maria Pina to ask her question. This is the benefit of having her as a panelist. So you can unmute yourself to ask if you would like.
Yes, I cannot open the video, but I think you can hear me.
Yes, we can hear you.
Yeah.
Yes, I was thinking to the population-based idea that Keith just described. And I understand that for let's say an industrial product like a wind turbine, industrial means that you can have several wind turbines that are similar. This is a great opportunity. I was wondering for a civil structure like a bridge, which is not a serious product. Of course, there are similar bridges, but most of the time you have one bridge, which is itself.
A unique design, I guess, something.
Sorry?
You mean it has a unique design, so it's not a repetitive.
So unique life, because you don't have, how do you call it for wind turbines when there are several fields of wind turbines, several wind turbines.
It's not a farm. It's not a farm.
Yeah, a wind farm. You don't have wind farm. I mean, bridge farms. So also the life of the bridge is different because the environmental conditions are different and so on. So it's more unique. I'm not saying that it's unique all over the world, but there is a very limited number of samples of that type. So how do you see this population-based idea for bridges? Because could be, I mean, a success if it could work.
So Chuck wants to say something, but I've got an answer as well. But Chuck, well, mate.
So I think there are certainly big challenges there because to some degree, just because of the terrain, you know, most bridges are individual entities and quite different, but I think there are also common components to bridges, the most common one being the cables on cable-stayed bridges. And there I could easily see everything that Keith says about the approaches Keith is outlining for population-based monitoring being able to be applied to those components of the bridge. All right, now, are there other components? Possibly, but that's the one that both suspension bridges and cable-stayed bridges, I think you could potentially apply this to the cables, monitoring of the cables.
So this is going to sound horrible again, basically, but the framework of population-based SHM that we're developing is based around the idea that you can only transfer information between structures if they are sufficiently similar to each other. And that's an easy question to answer if you've got a wind farm. All of the turbines are the same model, and the only real difference is in their foundations and the way they experience the winds and the waves, and whether or not they're in each other's wakes. Bridges, it's a lot more difficult. And so the way that we're looking at that is to regard structures as points in an abstract space. And then we can put a distance measure on this space, and we can actually decide if two structures are close enough to each other to try and transfer between them, right? Again, that sounds really messy, but I can give a concrete example here, and that was sort of a pun as well. So we've tried this out on 8 real bridges. We've tried it out on more than that, okay, but we're just writing up a situation where we've got eight real bridges, and we've put them in these spaces, and we've measured the distances between them. And what this framework allows you to do is to identify if you have 2 bridges, which parts of these two bridges are actually in correspondence and therefore would allow some sort of transfer and which are not, right? So to look at Chuck's example, if we had two cable-stayed bridges, this algorithm would say there is a correspondence between these bridges and it's in the cables. You can transfer information between the cables if you want, but not somewhere else, okay? We've got two beam and slab bridges where they're almost identical except in the way that they've been built into the road on either side of the motorway they're on, okay? I don't know the civil engineering terminology for this, but essentially they're the same bridge, but they've been connected to ground in different ways. This algorithm determines that these bridges are in correspondence everywhere except the boundary points, and that information can be transferred between the corresponding points. And it has worked surprisingly well on real bridges. So I have hope for this, actually. I understand exactly what you're saying, Maria Pina, because it is at the root of the problem. But it looks like there are ways forward with this.
Yeah, so you mean you go at the component level. It's not a similarity at the structural, at the global whole structure. It's a similarity of components. So you can build the pieces of your fault tree using different sets of bridges. I mean, you build the cable component using a set of cable-stayed bridges. And then you build, I don't know, the pier component of your model using other bridges or part of the previous, but all other bridges that have the same piers. This is the idea. I mean, it's building from components, not building the entire model of the bridge from a given set of bridges.
Yeah. It's a matter of identifying where you're allowed to move data, where you're allowed to move inferences. But the other thing that the population-based approach allows you to do is this. You can make a finite element model of a real bridge, and you know it won't be perfect, but you can treat that as a structure. And it will be in the population, it will be closer to the real bridge than a lot of the other real bridges that you've got. And so you will be able to make inferences from that as well. And you don't need to have a perfect updated finite element model of a structure to get some use out of it.
But if you, I mean, a lot of the effects you see in the real bridge, you might not have in your model unless you make your model very detailed. Like we heard about the environmental factors Chuck was talking about. No? So you'd observe this temperature variability in another bridge, but never in your finite element model, unless you really put it in. So using, I mean, and isn't that is also what Antonis is doing his PhD in this direction, so he's even better in telling this, but making these models to a level where they maybe are realistic enough is quite demanding, probably. Or do you think that, or in which way do you think?
Can I share my screen again? I don't want to hijack the conversation with population-based SHM just because that's a particular bee in my bonnet. But I can.
No, but it's super interesting. That's why we.
But I can show you some results for some real bridges if people are interested.
Yes, you could share.
Yeah.
Right, it might take me a minute to find it. Okay, so Chuck might have something to say while I'm finding this.
Keith, I'm gonna make you parallel process here because I was gonna ask you, can you take the operational and environmental variability, just like you described with, you could bring the finite element model in. It's not a perfect replication of any one particular bridge, but you can think of it as another one in your population. Can you think then of individual bridges under different environmental and operational conditions as just other replicates, if you will, in your population base?
Yes. Okay. Right. Eleni, my answer to that question is likely to start involving fiber bundles. And I don't know if people want me to do that.
Maybe if you show the visual, it helps. I don't know if just without any figure, it's easy to explain.
Yeah, it would be. Yes, the answer to that is yes, Chuck. We can try and build it into there's a way of looking at the geometry of structural problems that makes you realize that environmental and operational variations are something that can be projected out of structures, even in this space of structures picture. We're miles away from being able to do it, but I am hopeful that will happen. So I just want to show. I just want to show these results. Can people see this confusion matrix?
Yes, yes.
Okay, these are 8 real bridges. Okay, and essentially we've got a metric correspondence between these bridges. And it's built on the basis of a really sort of abstract framework, but these are real bridges, right? And there's, I can probably show some pictures of the bridges if people want, but there's 2 beam and slab bridges, 2 truss bridges, 2 suspension bridges, a cable stayed bridge, and an arch bridge, okay? And this matrix shows their degree of correspondence. So the diagonal is a bridge being compared with itself, so they're all 1s, okay? Now what Maria Pina said is absolutely right. Bridges are unique, and they don't, you know, they don't always look like each other very much at all. And that's why these correspondences are all fairly small, cross correspondences. But you can see that there are some where they're not small at all, okay? There's a 0.51 there and there. And that is between beam and slab bridge 1 and beam and slab bridge 2. And that is the one where they were very much the same construction, except what happened at the boundary conditions, the places where the roads joined. The other good correspondence here is between 2 suspension bridges. And this actually illustrates nicely what Chuck was saying. This high value, 0.47, pretty much comes down to the cable structure, okay? Now, the interesting thing here is that we've got 2 truss bridges, which are very similar in construction. And they come out at a 0.95 correspondence. Now, depending on the way the theory works out, it might be that we decide that a correspondence of 0.9 is enough to try and transfer information. In which case, we'd probably have a go at transferring information from this truss bridge to this truss bridge, but we wouldn't necessarily try with any of the others. Now, using all of this metric stuff, if I can build a finite element model that, considered as a structure, comes within 0.9 of the real structure, then I would think it was worth transferring the information from it. Is that reasonable? I'll stop there.
Keith, since you're showing the confusion matrix, maybe to ask you, both you and Chuck, it is often the case when we're trying to use machine learning that we get caught in this, you know, the use of the confusion matrix and making sure that everything is identified fully. When my experience is, in many cases, perhaps for the decision, it doesn't exactly, it's not so important if everything is fully identified, but rather if you can tell whether, for example, there is a probability of damage that is above, whether, you know, maybe you have 3 levels of damage, and it's enough to understand whether you are above level 1, for instance. And maybe the confusion matrix, although split, is highly successful in identifying this condition. So is this something that maybe, you know, we should be, as probably goes along the lines of what you showed, Kit, but do we need a new type of matrix that is indeed is a decision matrix and not the confusion matrix of the absolute detection?
I think what you're saying is right. We should actually go by the decision matrix. So if in that example that I showed in the talk, the actual classifier on the damage state was only 60% accurate. Okay. But that was actually at the second stage of the decision process. The first stage of the decision process was a novelty detector that tried to work out if it was damaged or not. Okay. Now, because the decisions you had to make were just do nothing or do something, the fact that you accurately spotted that there was damage allowed you to make the right decision. You didn't need to know what the details of the damage were.
Yeah, so it's along the same.
So the classifier was only 60% accurate, but the decision maker was 94% accurate.
And maybe then to ask also Chuck a bit on this, because you know, the machine learning, as you showed in your slides, has been used for SHM already since the 2000, I guess, when you started looking at the pattern recognition sort of perspective. And, you know, SHM has been met with a lot of criticism on the applied side. But my observation is that now, with all the hype surrounding deep learning, which has always been around, let's say, I mean, machine learning has always been around for us, people start getting more convinced that if you throw them a tool that has the title deep learning, it will work, as opposed to convincing them that using, you know, already the approaches that have been developed in the SHM context probably is more robust. And so to me, this is a bit of an oddity, because it goes along the lines of what Chuck mentioned. So we need to produce tools that do not require a PhD, sure, to be used. But it looks like the hype has been convincing people to adopt things that are much less probable and more readily right now. So what is your opinion on this? And does it mean something for SHM? Can it be exploited?
I can give an opinion and keep it at that. Is that, you know, any of these machine learning tools rather are only as good as the training data that you have available. Mm-hmm. All right, I don't see the deep learning as being a magic bullet that compensates for lack of quality training data. So, and I almost look at it as even a black box approach than more traditional approaches, where we have to put a little bit of thought into what are the features that we're going to use. And the more you, again, can bring a physical understanding of how your system is going to change as a result of the damage you're looking for, the better you can do on selecting the features that you're feeding into the process. And you know, I've seen some things with the deep learning where the idea is to get away from the feature extraction portion of the process. And maybe with the sufficient training data, that's an appropriate approach. But I still think you're going to be better off with a physical understanding and using that physical understanding in your process.
So can I just make, so we know there's a massive difference between academic SHM and real SHM, the implementation of the ideas in the real world. So there are a million papers about SHM because academics need to publish papers. And the amount of actual shining real world examples of SHM are fairly small. And I think what we're seeing a bit over the last 5 to 10 years is a massive interest in deep learning as a way of generating papers in the academic community. Whether or not that translates into real world SHM is going to be another matter. And I think what is actually going to happen, and I'm going to be really opinionated now, is that the good things that you can do with deep learning are going to be unpicked. People are going to work out what is real and what is hype. And then some of that good stuff is going to end up ultimately getting into real world SHM systems. But the amount of interest that the academic community shows in deep learning is not necessarily an indicator of how well it's going to turn into real world applications. Did I answer a question then, or did I make one up and then answer?
Yes, that's what I meant. What does this mean about, you know, the actual practical value of, and acceptance of SHM?
May I comment on this? I completely agree with you, Kit, about this, academic value of these papers or methods on deep learning for damage detection. I completely agree. But if you consider for example, the effect of environmental conditions or the monitoring of forces, I mean, things that you can actually measure, because you can measure the variation of temperature, the variation of the height of the water in a river, or something that you can measure. Well, maybe in that case, these machine learning, deep learning approaches can have a value. I'm not working on this, so I'm talking about something that I don't know very well. But I mean, from the philosophical point of view, since we can get data on these quantities, maybe it can work.
I think if it's backed up by physics, okay, I think we can use, I think we should use physics to understand which problems we should or shouldn't try to solve with machine learning, maybe. So for example, if you look at some deep learning architectures like convolutional neural networks, they've turned out to be really, really good at speech problems or image problems. Yeah. But there's not necessarily any justification for pushing an FRF into one of these algorithms, and unless you're very, very carefully constrained what you're doing. But if your SHM problem can be translated into an image recognition problem, so for example, if you've got mobile agents taking film of structures and you're looking for cracks, for example, then an image recognition system based on a deep learner will probably do that really, really well, because that's what they do really, really well. But you shouldn't necessarily, I really worry about the thing that Chuck alluded to earlier, which is the idea that something like a convolutional neural network is a powerful tool because it will implicitly extract features within its structure. And I just worry that if you use that instead of putting any physical or engineering insight into a problem, you're asking for trouble. I think if you put all of the engineering and physical insight that you can into a problem and then mop up the stuff that you don't know with a machine learner, that's probably the most responsible thing you can do.
Yeah.
I think that we should slowly move to an end, and we can still keep on going informally, but but there was one point that in Chuck's presentation where he quickly wanted to address that, I mean, I guess as an academic, but because he showed this completely opposite approaches from practice and academia, and at least I got the impression that this was considered to be something that we should somehow fix. But I guess, I mean, my viewpoint is that, of course, there are problems I'm sure there are things we can improve, but I guess that this opposite approach is actually a strength in this whole thing. So the fact that we, I mean, and sometimes in engineering, it's, you know, I think some of the engineering education actually is quite case-based, and sometimes too much, because I think as an academic scientific education, you should try to be general. Actually, my students, they really often love very practical industrial case studies as master theses. And I always tell them, you know, you can do that for 40 years of your life when you leave that university. So for the last time, you have the chance to do something general. And isn't that what we should actually do at universities?
Can I just say that I didn't intend any disrespect to academic research?
No, but this was to Chuck.
It was me that made the mistake, Keith. No, so let me, and I was trying to be cognizant of time, so I can't go into more detailed discussions on any of those. But, you know, I'm fully aware too of the fact that if you probably did these really focused things on a specific industry problem, you probably would struggle to get those published in a journal. Okay, because they're too narrow, they're too focused. Okay, there is this issue of having to look at the problem in a more general approach, you know, demonstrate it on some examples, that type of thing. So, you know, I made it really black and white in my presentation, but it's much grayer than that in reality. Okay, there's, you know, so maybe you could say some of the academic publications could be a little bit more focused, you know, tied in with an industrial, but if they get too far in that, they're not going to get published, probably, would be my concern. All right, so you know, please take that as it's a lot grayer than maybe the red and white that I used in my slide.
No,
I'm not saying that we shouldn't write papers, right? That's how I feed my children. But at the end of the day, I'm a theoretical physicist dreaming of being an engineer, basically. At the end of the day, stuff has got to work, right? Or else it might as well be pure maths. It has to work. And so I think all of this stuff has got to fit together. You know, the maths, however abstract it might appear to be, might be useful. It might get us somewhere. And so it's worth looking at that. But at the end of the day, we can't judge engineering on the beauty or not of the equations we're using, right? You can get away with that in string theory to an extent, but you can't get away with it in engineering. So it is really a multidisciplinary problem for people at all ends of the spectrum of abstraction. And it's all got to fit together if it's going to work, I think.
Maybe this is a good point to ask you for concluding remarks. So if you would like to leave the audience with a closing statement, what would this be? Maybe we start with Chuck, who was first.
All right, so you could say that mine was kind of a negative presentation because I listed all these challenges or drawbacks, limitations, what have you. I don't think you should look at, particularly because we probably have a lot of students who are listening. I don't think you should look at that in any way as negative. I think that it should be looked at as these are challenges, and challenges for the current students, researchers to address. I don't think they're necessarily insurmountable in any way, but it's always good to acknowledge what the shortcomings of your technology are. And that, I think, helps guide people in the research directions that they take. So I would just like to say, don't take everything that I did as really negative. It's actually, look at it as an opportunity. Would be the words I would give to the students who are participating.
Mm-hmm.
So I guess what I'd say about my presentation was that it might have looked just like a load of maths that I was enthusiastic about. And in fact, that's what it was. But underlying that is, I do think that some of this stuff will turn out to be useful. And what we've got to do is to keep doing this stuff, basically to find the, you know, the diamonds in the mud, you know, which is just as well, really, because that is exactly how I have been feeding my children for the last 30 years. So it's worked out okay for me. But I think that's the way we're going to do things, right? If SHM isn't working for whatever reason, in practical terms, if we've not got it on all of the bridges and all of the aeroplanes, and, you know, we've got to keep looking for the missing ingredient that's going to help us do it. And I'm looking for it in interesting bits of maths and physics. Other people are looking for it in interesting pieces of sensor technology, and other people are looking for it in, you know, interesting macroscopic physics like guided wave scattering. None of this is wasted. You know, if one or two things work, it'll get us where we need to go.
As our co-organizer is a student, Adonis, and I see he commented on the, maybe you can also give us your perspective on whether this is a negative or a positive encouragement.
Well, what I wrote was that I was particularly inspired by the talk and by the challenges addressed, and I didn't find it negative in any way, because yeah, it was mentioned specifically to students to comment. Yeah.
So thank you, I guess, both for this, which ended up being an inspirational talk, both as I see Antonis and Maria Pina commenting. Maybe Daniel, we would like to wrap up so we release the audience.
No, I can also just say that it was inspiring, not only for students, but also for professors, as Maria Pina and myself can say. And it was a great perspective, great talks. Nobody will not be locked up. I think this we will not get. Also maybe better like that. Thanks a lot for your time and your insights, and yeah.
And thanks everyone for joining. Our last installation comes very soon. Maybe Adoni, you tell us the date. July 8th.
Next week.
Yes.
Yeah.
Next week.
First day. Yeah.
Thanks a lot for inviting us.
Yeah.